Hello students, welcome to my lecture. Here we will be discussing about metric spaces. Okay, so let's discuss about metric spaces. So you can see the definition of metric space here. Let X be a non-empty set. A function d from x cross x to R is said to be a metric on X if it satisfies the following properties. Okay, so we have a non-empty set X. Okay, and we have a function from where to where, from x cross x to R. Okay, that means from the Cartesian product of this x to itself, x cross x to the set of real numbers. Okay, that function is denoted as d. Okay, if this function satisfies these four conditions, if this function satisfies these four conditions, we can say that that is a metric. That function d is a metric on x. Okay, look at the first condition. The first condition, d of xy greater than or equal to 0 for all xy belongs to x. Okay, that means if you take any two elements from the x, okay, from capital X. First one is capital X denoted as small x, and second one is denoted as small y. Okay, the distance between them, or the function, the value of function between them is always greater than or equal to 0. Okay, we cannot find a negative value. Okay, we cannot find a negative value for this x comma y. Okay, we know that all the elements in x cross x are in ordered pair form, right? Ordered pair form, because it is a Cartesian product. It is a Cartesian product. Okay, so all the elements in x cross x will be in which form? In ordered pair form. Okay, so you can take any ordered pair like this x comma y. Then for that x comma y, that function value will be greater than or equal to 0. You cannot find a negative value for any ordered pair in this x cross x. Okay, that is the first condition. Then what about second condition? Second one, d of xy equal to 0 if and only if x equal to y. Greater than or equal to 0, right? D of xy is greater than or equal to 0 from the first condition. So in this, according to this condition, it can be equal to 0 also. Greater than or equal to 0 means two possibilities. One greater than 0, another one equal to 0. Okay, so equal to 0 can also happen. Okay, that's what you can see in this second case. That means d of xy equal to 0. It can be equal to 0 if and only if x equal to y. Okay, that means d of xy will be equal to 0 only in which case? Only if x equal to y. If x and y are different, you cannot find d of xy equal to 0. D of xy will be different. Okay, or if d of xy is not equal to 0, then definitely x will be not equal to y. Okay, if d of xy equal to 0, that means x will be definitely equal to y. Or if x is equal to y, then d of xy will be equal to 0. Okay, that is the meaning d of xy equal to 0 if and only if x equal to y. Okay, now move to the third condition. D of xy is always equal to d of yx for every xy belongs to z. Okay, sorry, for every xy belongs to capital X. That means if you take any two ordered pairs, okay, if you take any two x comma y from the capital X, the d value of that ordered pair x comma y will be equal to the d value of ordered pair y comma x. Okay, if you change the order between x and y, it won't change the value of the function. Okay, d of xy is always equal to d of yx. Even if you change the order, the value will be same. It is like a distance. Okay, the distance between Mumbai and Bangalore, that is same as the distance between Bangalore and Mumbai. If you change the order between them, the distance won't change. Mumbai and Bangalore, Mumbai to Bangalore, and Bangalore to Mumbai, both are same only. Okay, distance is same like that. That is the third condition. Next, we have fourth and last condition, that is known as triangle inequality. Okay, this condition is known as triangle inequality. Triangle inequality. Triangle inequality. Okay, according to this condition, for all x, y, z, belongs to capital X. Okay, that means here we are taking three elements from this capital X, Y, Z. Okay, and this relation you can see for all X, Y, and Z from capital X. Okay, according to this one, d of xz will be less than or equal to d of xy plus d of yz. Okay, d of xz will always be less than or equal to d of xy plus d of yz for all x, y, z belongs to capital X. It is known as triangle inequality. Okay, because in a triangle we can say that sum of any two sides will always be greater than the third side. Okay, it is like that property of triangle. Okay, so if this function d satisfies all these conditions, we can say that d is a metric on X. Okay, that d is a metric on X if it satisfies all these conditions. Okay, I hope it's clear. Yes. Then if d is a metric, that means it satisfies all these conditions, we can say that the x comma d is a metric space. Okay, we have a non-empty set capital X, and in that X we have a metric small d, and this capital X and that metric small d together constitute a metric space. Okay, yes. So what are the requirements for this metric space? First, we need a non-empty set capital X. In that, we need a metric small d, which satisfies all these four conditions. So we can say that this X and D constitute a metric space. Okay, so that is the meaning of metric space. Okay, let's see. Let's move to the next case, that is discrete metric. Okay, discrete metric. Here we discussed what is meant by a metric. Okay, what is meant by a metric we discussed. It should satisfy these four conditions. Let's move to a special kind of metric, a special type of metric known as discrete metric. Okay, from the name you can understand it is a metric itself. Discrete metric means it's a metric only. Okay, from the name itself that metric is coming. So this is a metric. It satisfies all these four conditions, but it's a special kind of metric, not an ordinary metric. Okay, that's why the name discrete metric. It's a special kind of metric. See, what is that specialty? You can see here the definition of discrete metric. You can read here. Let X be a non-empty set. A map D from X cross X to R defined as D of xy equal to 0 if X equal to Y, and that D of xy equal to 1 if X is not equal to Y. It's not equal to 1, not equal to Y. Okay, then that D is called discrete metric on X. Okay, then that D is called discrete metric on X. Okay, so this is the definition of discrete metric. Okay, that means discrete metric can take only two values, either 0 or 1. Okay, its range consists of only 0 and 1. Okay, so here we have only two possibility. If you take d of xy, if you take two elements x and y from capital X, either they are equal or they are not equal. If they are equal, the value of the function is 0. If they are not equal, the value of the function is 1. Okay, such a metric is known as discrete metric. Okay, next, in the next step we will prove that this is a metric. Okay, currently this is the definition. Okay, now by this definition, in the next part of this video, I will show how this is a metric. Okay, you can see a function here. Okay, you have a non-empty set capital X, and there is a function d from x cross x to R, and I told you it is known as discrete metric. Discrete metric means it should be a metric, but how can we say that it is a metric? It should satisfy these four conditions. If it satisfies these four conditions, we can say that it is a metric. Okay, that proof you can see here. This satisfies these four conditions. Okay, this function defined like this, defined here, satisfies all these four conditions of metric. That's why this is also a metric, a special kind of metric. Okay, see, how can we say that it is a metric? How can we say that it is satisfying all the four conditions of a metric? Look at the first condition. What is the first condition for a metric? D of xy must be greater than or equal to 0. Okay, d of xy must be greater than or equal to 0. That is the first condition for a metric. See, that also you can see here. That condition is satisfied here. Okay. See the first part. By definition, d of xy is greater than or equal to 0 for every x comma y belongs to capital X, right? That means that first condition, d of xy is greater than or equal to 0. By definition itself, you can understand that condition is satisfied. Okay, see what are the possible values of d of xy? D of xy can be either 0 or d of xy can be 1. Either 0 or 1. 0 or 1 means it is always greater than or equal to 0, right? 0 is equal to 0, 1 is greater than 0. So that means it is always greater than or equal to 0, means first condition is satisfied. Okay. Next move to second condition. What is the second condition for a metric? D of xy equal to 0 if and only if x equal to y. Okay. D of xy is equal to 0 if and only if x equal to y. Okay. That also you can see here. Second part. That also you can see here. Okay. See, for x comma y belongs to capital X. What will happen if x equal to y? If x equal to y, then d of xy will be equal to 0, right? Same definition you can see here. If x equal to y, then d of xy is 0. Okay. See here, what will happen if x is not equal to y? If x is not equal to y, then d of xy equal to 1. That is not equal to 0. Okay. That means if x equal to y, then definitely d of xy equal to 0. If x is not equal to, what will happen? Then according to the definition, d of xy is 1, not equal to 0. Okay, so d of xy is 0 if and only if x equal to y. In this case also, if x equal to y, then definitely d of xy equal to 0. Okay, and if d of xy equal to 0 means definitely x equal to y. Okay, so that second condition also satisfied here. Second condition of metric. Okay, now move to the third condition. What is the third condition of metric? D of xy equal to d of yx for every xy belongs to x. Let's see how this condition is being satisfied here. For xy belongs to x. Okay, let's take any two x comma y belongs to capital X. Okay, so here we have two possibilities. Okay, we have two possibilities. If you take any x and y from capital X, we have two possibilities for that. This is the first one. If x equal to y, first possibility means x and y are equal. Okay. Second possibility means what? X and y are not equal. They are unequal. That is second possibility. Okay. Now we will prove that for these two cases, for these two possibilities, you can see this third condition is also satisfied. First condition x equal to y. Second condition x not equal to y. In both of these conditions, you can see that d of xy and d of yx are equal in this case. See here. Look at the first condition. If x equal to y, if x equal to y, then what is d of xy? By definition, according to the definition of discrete metric, if x equal to y, then d of xy will be equal to 0. Okay, then what about d of yx? That is also equal to 0 because x equal to y means y equal to x also. Okay, so d of yx is also what? 0. So d of xy is 0, d of yx is also 0. That means d of xy and d of yx are equal. Okay, the third condition is satisfied here. D of xy and d of yx are equal if x equal to y. Okay, if x and y are unequal, this condition is satisfied. D of xy and d of yx are equal. Next, we can see that if x not equal to y also, this condition is satisfied. Okay, it is not violating that condition even if x and y are different. See here, if x not equal to y, then what is d of xy? By definition, d of xy equal to 1. If x and y are different, by the definition of discrete metric, d of xy equal to what? 1. And what about d of yx? X and y are different means y and x are also different. So d of yx is also what? 1. See, d of xy is 1, d of yx is also 1. That means d of xy equal to d of yx if x and y are different, if x not equal to y. Okay. See, that means our third condition is also satisfied. In both the cases, you can see we have only these two possibilities, either x equal to y or x not equal to y. In both the cases, you can see that d of xy and d of yx are equal. Okay, that means the third condition is also satisfied here. Okay. Now move to the fourth one. What is the fourth condition for a metric? Fourth condition is triangle inequality. D of x set less than or equal to d of xy plus d of yz for all xyz belongs to capital. This also we can prove here. This condition is also satisfied here. Okay, we can see here. For that we have 5 cases. Okay, we will prove this using 5 cases. There are 5 possibilities here because we are taking 3 elements from capital X, Y and Z. So regarding their equality, we can see 5 cases like X and Y are equal but Z is different. X and Z are equal but Y is different. Okay, like that we have 5 cases. 5 cases. Let's see which are the 5 cases. Fourth one. Okay, for X, Y, Z belongs to capital X. We are taking 3 elements from capital X, Y and Z. Okay, see case 1. Case 1. Case 1 means X equal to Y equal to Z. I told you we have 5 cases. And this is the first case. In this case, X equal to Y equal to Z. In this case, we will show that, or we will see that this satisfies the fourth condition of metric. And not only in this case, in the upcoming 4 cases also, you can see the same. Okay. Now see how this fourth condition is satisfied in this case, in the case 1. That means if X equal to Y equal to Z. Okay. Yes. Now, if X equal to Y equal to Z, then what is d of xz? That is 0 by the definition, because X and Z are equal. So d of xz equal to 0. Okay, what is d of xy? That is also equal to 0 because x equal to y by the definition. So d of xy is also equal to 0. Okay, what is d of yz? That is also equal to 0 by the definition because y and z are equal. Okay, so d of xz equal to 0, d of xy equal to 0, and d of yz is also equal to 0. Okay, see, in this case, what is d of xy plus d of yz? D of xy is 0 and d of yz is also 0. So d of xy plus d of yz means 0 plus 0, 0 only. Okay. So d of xz is 0, d of xy plus d of yz is also 0. So we can write d of xz is equal to d of yz, sorry, d of xy plus d of yz because both are 0. Okay. So yes, d of xz equal to d of xy plus d of yz. And this can be written in this form also, right? D of xz less than or equal to d of xy plus d of yz, because equal to means less than or equal to, right? Less than or equal to means this equality is also included here. It can be either less than this or equal to this. So that means this equal to is equal to comes under this. Okay, so no problem in writing this one in this form. Less than or equal to means equal to is also included here. Here we got equal to. So this can be written in this form. This is what? This is nothing but our triangle inequality. Our triangle inequality. Okay, d of x, the fourth property, d of xz less than or equal to d of xy plus d of yz, the fourth property for metric. Fourth property, the same thing you can see. Okay, d of xz less than or equal to d of xy plus d of y. Okay, so we can say that the fourth condition of metric is satisfied in case 1. Let's see the same for case 2. This is case 2. You can see case 2. Okay, case 2 means x not equal to y equal to z. X not equal to y equal to z. That is case 2. Okay. So in this case, what is d of xz? D of xz will be equal to 1 because by definition x and z are different. Okay, y and z are equal and x is different from y. So x is different from z also. So x and z are different. They are not equal. X is not equal to both y and z because y and z are equal. X is not equal to y. That means x is not equal to z also. So x and z are different means d of xz will be 1 according to the definition of discrete metric. If they are different values, their function value will be 1. Okay. Similarly, what is d of xy? See, x and y are also unequal here, different. So d of xy will also be equal to 1. Okay. What is d of yz? D of yz, y equal to z, right? Y equal to z. So if these two values are equal, their function value will be 0 by definition. D of yz will be 0. Okay. So what is d of xy plus d of yz? D of xy is 1 and d of yz is 0. So d of xy plus d of yz means 1 plus 0, that is 1 only. Okay, that is 1. Okay. See, what is d of xz? That is 1. What is d of xy plus d of yz? That is also 1. That means both are equal. D of xz will be equal to d of xy plus d of yz. That's what you can see here. D of xz is equal to d of xy plus d of yz. Okay. So this equality can be written in this form, less than or equal to, because this is equal to. Equal to is also included here, either less than or equal to. So we can include equal to here also. Okay. So this is nothing but triangle inequality. D of xz less than or equal to d of xy plus d of yz. That is our triangle inequality only. The fourth condition of metric is satisfied here also, in case 2 also. Okay. Let's see the same in case 3. Let's see the same in case 3. Case 3 means x equal to y not equal to z. Okay, x equal to y not equal to z. So what is d of xz? Okay, z is different from x and y. X and y are equal, but z is different. So z is different from x. So d of xz will be 1 according to the definition of matrix. Okay, what is d of xy? D of xy will be 0 because x equal to y. So d of xy will be 0. Okay, what is d of yz? D of yz will be 1 because y and z are different. According to definitions, d of yz is 1. Okay, so tell me what is d of xy plus d of yz? D of xy is 0 and d of yz is 1. So 0 plus 1, 1 only. Okay, so d of xy plus d of yz is 1 and d of xz is also equal to 1. That means both are equal. D of xz is equal to d of xy plus d of yz. That's what you can see here. D of xz is equal to d of xy plus d of yz. Equality means it is less than or equal to also. Okay, like the previous two cases, d of xz less than or equal to d of xy plus d of yz. That means the triangle inequality is satisfied in case 3 also. Okay, in case 3 also. Now we have last two cases, case 4 and case 5. Let's see our case 4. Case 4. That means x equal to z but different from y. X and z are equal and y is different from both of them. Okay. In this case, what is d of xz? D of xz equal to 0 because x and y are different. Y is different from both x and z. So d of xz will be equal to 0. Sorry. D of xz. What is d of xz? Will be equal to 0 because x equal to z, right? X equal to z. If x equal to z, by definition, d of xz will be equal to 0. Okay, by the definition of discrete metric. So, if d of xz will be equal to 0. D of xz will be equal to 0. Next, what is d of xy? See, x and y are different because y is different from both x and z. So, x and y are different. So, d of xy will be equal to 1. Okay. Similarly, d of yz is also equal to 1 because y and z are also different. Okay. Yes. Okay. So d of xz equal to 0, d of xy equal to 1 and d of yz equal to 1. Okay. Now what is d of xy plus d of yz? D of xy is 1 and d of yz is also 1. So 1 plus 1, 2. D of xy plus d of yz is 1 plus 1 equal to 2. Okay. So in this case, d of xz is what? 0. And what is d of xy plus d of yz? That is 2. We know that 0 is less than 2, right? So d of xz will be less than d of xy plus d of yz. That's what you can see here. D of xz is less than d of xy plus d of yz. Okay? Less than means less than or equal to, right? Because less than or equal to means in that less than is also included. Okay? Like we can include equal to there, less than is or is less than is also included. Less than or equal to means both less than and equal to can come. Okay, so less than means less than or equal to. So d of xz less than or equal to d of xy plus d of yz. That means the triangle inequality is satisfied in case 4 also. Okay, I hope it's clear. Now move to the last case, case number 5, the final case. X not equal to y not equal to z. Okay, x not equal to y not equal to z. That means all are different from each other. So all the function value will be 1. X, Y, Z all are different. So d of xz is 1, d of xy is 1, and d of yz is also 1. All are different from each other. Means all function values are 1. Okay. Yes. So what is d of xy plus d of yz? D of xy is 1, d of yz is also 1. So d of xy plus d of yz means 1 plus 1, that is equal to 2. Okay. But d of xy is only 1. But d of xy plus d of yz is 2. 1 is less than 2, right? So d of xz will be less than d of xy plus d of yz. That's what you can see here. D of xz less than d of xy plus d of yz. Less than means less than or equal to. Okay. So d of xz less than or equal to d of xy plus d of yz. That means the triangle inequality is satisfied in this fifth case also. Okay. You can find only these five cases. First one, case 1, x equal to y equal to z. Okay. Second case, x not equal to y equal to z. Okay. Third case, x equal to y not equal to z. Okay. Next, fourth case, x equal to z not equal to y. Okay. And the last fifth case, x not equal to y not equal to z. In all these cases, we proved this triangle inequality. D of xz is less than or equal to, always less than or equal to d of xy plus d of yz. Okay, here x, y, z are arbitrary elements. So this is true for all x, y, and z from capital X. That means this is a metric. Okay, this is a metric. This D defined like this: d of x y equal to 0, if x equal to y equal to 1, if x is not equal to y, is a metric. Okay, that's why the name discrete metric. It's a special kind of metric. Okay, I hope it's clear. Okay, we will discuss more about metric space in the upcoming videos. Okay, thanks for watching. Bye bye.